Okay, so welcome to 4.3 covalent structures. So in the last unit we looked at covalent bonding, and now we're going to apply that covalent bonding to look at some structures which incorporate that particular type of bonding. So by the end of the unit you should be able to do Lewis electron dot diagrams, understand the octet rule refers to a certain thing. Some atoms don't actually follow the octet rule, so remember it's only a rule of thumb. Resonance structures occur when there's one possible position for the double bond to occur in a molecule. Repulsion of electron pairs determines shapes of species, and we'll look at something called the valence shell electron pair repulsion theory, or VSEPR. And from last year, I'm sure, carbon and silicon forming these network covalent structures. And you should also be able to deduce electron dot Lewis diagrams, use valence shell electron pair repulsion theory to determine molecular shapes, predict bond angles also using VSEPR, predict molecular polarity from bond polarity and molecular geometry, which we touched on a little bit in the last unit, and deduce resonance structures and give examples like benzene, or aromatic rings at least, and ozone, and explain the properties of these giant covalent network solids. Right, so let's just get into it. So you're probably familiar with this from last year, just kind of revising it. So Lewis structures are representations of molecules showing all the electrons bonding and non-bonding. And each bond contains 2 electrons, as we discussed last unit. Okay, so a single bond is essentially just 2 electrons being shared. So elements pair up according to the octet rule, which basically is a rule of thumb saying that elements love to have their valence shells to be full, okay, to have the electron configuration of a noble gas. And we provided chlorine here as the example. So both chlorines take, or at least share, sorry, taking is ionic, both chlorines share an electron, so that means they both have full outer shells, and I guess in some anthropomorphic sense they're happy. So how do you draw Lewis structures deductively? Okay, so I'm just going to go through a step-by-step procedure on how I do it. Okay, so the first thing you do is draw out the atoms with the least occurring atom as the central atom. So if this wasn't oxygen and say sulfur dioxide, then sulfur would be in the middle, because sulfur's less, 1 is less than 2, and sulfur dioxide is only 1 sulfur. Okay, then you put in the valence electrons. Okay, so oxygen has 6, and then you connect up 1 bond from each of the outside atoms to the central atom as so in step 3. Okay, and then 4, count the electrons to see if all the atoms now follow the octet rule. Okay, so quite clearly they don't, okay, because oxygen only has 7 now, doesn't quite work, and that's where step 5 can come in. If not, then add extra bonds until they do. So that's why oxygen has basically a double bond, because it needs to share 2 electrons with the other oxygen for it to now have 8 around its outer shell and be happy, if atoms can really be happy. So if this can't be done and still you have not got a full octet shell, then you can develop something called a coordinate covalent bond, which is what we looked at briefly in transition metal chemistry. And this is where one atom now donates both of the electrons to the bonding pair. Okay, so carbon monoxide is the case here, where oxygen donates both its lone pair of electrons to the bond. And then step 7, create up the structure making. So it's easier to read. Okay, so you put the electrons in pairs. For one atom you use O's, the other atom you use X's. Okay. You'll notice, of course, too, that the structural formula here, that you have this arrow here for the 3rd bond, because that's a coordinate bond. Okay, oxygen's actually given both its electrons. So, like all things, there's exceptions to the octet rule, and one example is boron. Okay, so boron forms stable compounds with just 3 valence electrons. However, these compounds are very highly reactive. I use them in my PhD, and indeed they are. They're quite reactive with the atmosphere and tend to combust. Okay, so you use them under inert atmospheres. And also not only boron, but beryllium. Okay, beryllium forms stable compounds, not with 3, but 2 valence electrons. And compounds that break the octet rule are often toxic and dangerous, as I just said in the last slide. So be ready, so that they're ready to react, so the octet rule is obeyed. Okay, beryllium compounds are also very reactive. So here's some other examples of octet rule here, and the use of Lewis dot diagrams. Okay, so you see in the oxygen that both oxygens now have 8 because they're sharing 2 electrons. Nitrogen has this triple bond, okay, because again it's the octet rule by sharing 3 electrons. Carbon dioxide has these double bonds because they are sharing, the oxygen shares 2 and so does the carbon for each. And hydrogen cyanide, where the nitrogen shares 3 and the carbon shares 3. Another examples here are ethene, ethine, carbon monoxide, ammonium, and H3O+. So I want you to pause the video now and see if you can draw carbon monoxide. We've actually looked at it already in previous slides, and we're going to look at the structure of hydronium H3O+ later. So draw it and see if you get it right. Okay, moving along. So that's using the Lewis diagrams, dot cross diagrams, to work out structures. Okay, and in terms of structures, you also have to know shapes. Okay, so they are determined by the number of valence electrons of the central atom. Okay, so molecules don't exist in the 2D world, they exist in the 3D world. And so the 3D shape is a result of the bonded pairs and lone pairs of electrons. And this is where we use something called bilateral electron pair repulsion theory, or VSEPR theory, and it states the best arrangement for a given number of electron domains. Okay, so rather than call them electron domains, it's basically where the electrons are, so it's where the negative parts of molecules are, is one that reduces the amount of repulsion between these electron domains, or the amount of repulsion between electrons, basically. Okay, so as simply as possible, electrons don't like to be next to each other. We've already seen that in the last unit. Electron pairs are negative. They want to be anywhere near other electron pairs, okay, whether they're bonding or non-bonding. So they're going to repel, okay, like charges repel. So assuming the electron pairs are placed as far apart as possible, we can predict shapes of molecules. So if we look at the example here of ammonia, we have these bonding pairs, put that in the right place. We have these bonding pairs of electrons here, okay? And we also have this non-bonding pair. Now this non-bonding pair is going to start repelling the bonding pair between the nitrogen and hydrogen single bond. And it's going to start pushing it down. But then that's going to start repelling against these 2 electrons here, which I have, there we go, these 2 electrons here. So the most stable configuration for this guy is having the nitrogen on top, the lone pair on top, and the hydrogens kind of in a pyramid type shape, where the top of the pyramid is going to be the lone pair. Okay, oh, it's kind of a robot. Anyway, yeah, so it's kind of a lone pair. So that reduces the amount of repulsion between the electron pairs. Okay, so shapes are based on electron domains. An electron domain is basically the number of electron pairs, whether they be bonding or non-bonding, on a central atom. Okay, so the example I provided here is sulfur dioxide, which has 3 electron domains. So if you look at sulfur, which is a central atom, it's going to have basically this electron domain is domain number 1, this is domain number 2, and the non-bonding pair is going to be domain number 3. It's going to have 3 electron domains. Okay, whereas methane has 4 electron domains because it's got the 4 carbon-hydrogen bonds. Ammonia, which we just looked at in the last slide, because of that lone pair, has 4 electron domains. And ammonium also has 4 electron domains. This time, instead of a lone pair, you've got a hydrogen, which gives it its positive charge. So if you use the VSEPR model, this is how I would recommend it in 5 simple steps. So the first thing you do is draw the electron dot structure, identify what the central atom is, count the total number of electron pairs around the central atom, then predict the electron shape from that because you want to reduce the amount of electron repulsion. Okay, and predict the shape of the molecule using the bonding atoms. Okay, so if you this chart will help you, I hope, predict what the shapes are based around how many non-bonding and bonding pairs you have. Okay, so if you have 4 electron domains, you end up with a tetrahedral shape. Okay, an example from the previous slide is therefore methane for that. Okay, so if you have a lone pair on top, then that's going to look at the rule of thumb. Non-bonding electron pair bends it further by 2 to 3 electrons. 2 degrees. So that's going to be pyramidal, and that's going to be ammonia, which we looked at the last slide. And then we have the bent, where you have 2 bonding pairs and 2 non-bonding pairs in your 4 electron domains. And an example of that would be water. Okay, let's now look at 3 electron domains. So if you have a molecular shape where you have 3 bonding pairs, like boron trifluoride, it's going to be trigonal planar. Okay, or it's going to be bent, and that's the example of sulfur dioxide. Okay, that's the other one. If you have one of those bonding pairs being, one of those electron domains being non-bonding, and for 2 electron domains like carbon dioxide or carbon monoxide, it's always going to be 180. Okay. So shapes, if no non-bonding electron pairs. Okay, so that means that the shapes based around no lone pairs. So molecules or ions possessing only bond pairs of electrons fit into a set of standard shapes. All the bond pair repulsions are therefore equal. Okay, so you noticed in the last slide that if you have a lone pair, there's slightly more repulsion, which isn't bonded. A non-bonded electron pair, slightly more repulsive. Don't tell them that though. All you need to do is count up the number of bond pairs and choose one of the following examples. Okay, so 2 bond pairs are going to be linear, which gives you the bond angles. There's an example there. 3 bond pairs are trigonal planar, 120 degrees, because 360 divided by 3 is 120. Okay, tetrahedral, 109.5, like methane. If you have 5 bond pairs, which is something called trigonal bipyramidal, it's going to be 90 degrees and 120 degrees, like PCl5. And finally, octahedral, which we're familiar with from our work with transition metals, are all bond angles of 90 degrees. And SF6 would be an example of a covalent molecule with that. And if you have non-bonding electron pairs, like the case with ammonia, then what's going to happen is you're going to get slightly more distortion because there's extra repulsion caused by these lone pairs. Okay, so there's the animation there. So a bond pair repulsion is slightly less than a lone pair bond pair, and which is slightly less than a lone pair. Okay, due to this extra repulsion, the bond angles tend to be squeezed a bit more by about 2 to 3 degrees. Case in point would be methane here as an example. Okay, so carbon, 4 electrons pair up, hydrogen has 1 to complete the shell, so they've got 4 bond pairs, has to be tetrahedral. Okay, and the bond angles are all 109.5 degrees. Okay, because they've all got bonding pairs. Whereas ammonia, because it has that lone pair on top, is a little bit more repulsion. Okay, so it means the total number of electron pairs is 4 based on the tetrahedron, which we look at in methane, but because of the slightly more repulsion of the lone pair, then it's going to be something called pyramidal. Okay, so slightly less than 109.5, about 107. Okay, which we see now. Okay, so the shape of the base and tetrahedron, but because they're not all the same, these repulsions, the lone pair, which isn't bonded, is slightly more repulsive. Then the NH bonds are pushed a bit closer together, and the lone pairs are not included in the shape. Don't consider them. Okay, so it's going to be called pyramidal, and it's going to have an angle of slightly less than 109.5 due to that lone pair, which isn't bonded, 107 degrees in total. There we go. There's some wonderful diagrams illustrating that. Okay, water, again, the oxygen has 6 electrons, but it can't pair up with all of them. Okay, you've got these now 2 lone pairs. So you've got 4 electron domains based on the tetrahedron, but now you've got these 2 repulsive, highly repulsive lone pairs. So what's going to happen is that the lone pair repulsions are going to be a lot stronger than the lone pair bonding pair repulsions, which are going to be slightly weaker, slightly stronger than the bond pair repulsions. So the OH bonds are pushed even further down, they're squeezed together down, and that means instead of being 109.5, which you'd expect for a tetrahedron, it's going to be 104.5 between the 2 hydrogens which are bonded to the oxygen, and the shape is more bent or angular, because you don't, of course, include the lone pairs which are not bonded in the shape. Ammonium, which was an example. So again, tetrahedron, you'd expect that. Okay. Hydronium, which was the example that I wanted you to draw. That's what it looks like, because again, you've got that lone pair. But there's only 1 lone pair compared to water, so there's less repulsion. So it's now no longer 104.5, 105, it's now 107, closer to ammonia than it is to water. And you've also got the boromine trifluoride, another example. It's got 3 bonding pairs, 2 lone pairs, so those lone pairs are going to slightly repel. So it's going to be something called a T-shape, because you've got this massive repulsion from these non-bonding lone pairs, as you would expect. And sulfur dioxide, there's a little GIF there as well. The sulfur has 2 bonded atoms, but that 1 lone pair on top of the electron cloud. So it's basically going to push the bonding electrons down a little bit more. Okay. So it's going to be a little bit less than 109.5. And there's some examples from organic chemistry, with ethane being 109.5, ethene being 120 due to that bonding pair repulsion, and ethine being a straight molecule, 180 degrees. Carbon dioxide, however, is the shape of a compound with a double bond is calculated the same way. So that carbon dioxide now has double bonds. So we've just been considering single bonds. Okay. So double bonds behave exactly like single bonds for repulsion. So the shape will be the same as the molecule with 2 single bonds with no lone pair. So it'll be straight, linear, no worries. Then in terms of SL, we're kind of moved away. That's pretty much all you need for Lewis. For HL, we also have to look at resonance. Okay, so when a Lewis structure allows for the same arrangement of atoms, but different but equally valid arrangements of electrons, like sulfur dioxide, resonance occurs. So here's the example being ozone. The resonance hybrid is actually the dotted line below. Okay, so the electron's kind of smeared. There's 2 different forms of the ozone. There's one where you have a double bond here, and one where you have a double bond here. And really the state, it's kind of between these 2 states, and we call this delocalization. Important in organic chemistry later at university, because delocalization is an important part of aromatic chemistry. So these electrons are located in the p orbitals. The overlapping p orbitals create a new shape called something called the pi bond. Okay, which again we're going to look at more in later in the unit, but also in organic and a normal bond situation. And it's the resonance in these pi bonds that all overlap as well. Okay, these p orbitals can overlap. Okay, so nitrate's an example of delocalization. Okay, so you have 3 different, we call them resonance forms, okay, or resonance structures, and the Lewis structure therefore has three different Lewis structures. So you say that the nitrate has kind of electrons smeared along here, and that's double bonds, and not always in that double bond. The double bond basically moves. Okay. So we draw the resonance structures to more accurately reflect the structure of the molecule or the ion. And just to get your head around the way pi bonding works, possibly. So in reality, each of the 4 atoms in the nitrate ion has a p orbital. double bond of the NO double bond is normally a pi bond, and the p orbitals of all three oxygens overlap with the p orbital of the central nitrogen. So it's kind of a highway, a network of this one electron being funneled around in these resonance forms. So it just means that the pi electrons are not localized between the nitrogen and one of the oxygens, but rather they're kind of delocalized, smeared across the entire ion. Okay, so the classic example is benzene in organic chemistry. Okay, so benzene exists in two resonance forms, and so that's why we actually draw benzene with a circle in the center, because that's like the average of the two resonance forms. Critical for its reactivity, which you'll learn about later. Okay, so the organic molecule benzene has a p orbital on each of the carbon atoms, kind of poking up. Okay, and it means that the electrons can jump and delocalize around and below as well, below the structure. Okay, so they're not actually positioned in on one of the carbons, they're actually delocalized around all of the carbons. Okay, this even distribution of pi electrons in benzenes gives it an extra stability you would not expect if there wasn't this resonance, this delocalization. Carbonate is another example. So you've got the pi bond, meaning that the electron is delocalized, and you'll notice also that the charge, so it's basically that the negative charge is also shared on all the oxygens, so they're all slightly negative. Okay, and these are the three resonance forms, which really should be in square brackets. So that's resonance forms. We'll now look at something called allotropes, which are particularly around carbon, which you would have touched on last year. So allotropes are compounds of the same element, but they have different structures. And carbon is the classic example. Okay, so carbon can create three different structures: diamond, the girl's best friend; graphite, great for pencils; and Buckminsterfullerenes, which are used also in nanotubes. So looking at diamond, so in diamond, each carbon is bonded to 4 carbons. Okay, and for HL, carbons are bonded by the sp3 hybridization to 4 other carbon atoms, forming a giant network covalent compound. Now, we've briefly touched on sp3 hybridization ideas. We'll look at that in more detail later. But yeah, all you need to know now at the moment is there's something called sp3 hybridization, and that's how they are bonded in diamond. Okay, and because of these, every carbon bonded to 4 adjacent carbons, diamond has a high melting point because you've got these strong directional covalent bonds to each carbon. It's extremely hard because you've got to break all these carbon-carbon double bonds. It doesn't conduct because there's no free electrons, and it's insoluble because the molecular bonds between the carbons are stronger than any of the intermolecular forces that want to break it up or dissolve it. The second allotrope is graphite, where this time, instead of being bonded to 4 carbons, they're bonded to 3 carbons. Okay, so we don't call it an HL just saying, oh, they're bonded to 3 carbons. We call this sp2 hybridization in HL. Again, don't have to worry about it at the moment. We'll go into this in more detail as we move on through the unit. But what happens basically is that you have these sheets of carbon, and that the p orbitals of the carbon are perpendicular with the plane of the ring. Okay, and this is the graphite structure. So carbon has 4 valence electrons because it's in group 4. Okay, so we know that 3 are bonded, 3 involved in bonding, so 1 has to be delocalized around the p orbitals, and this means that this presence of the p orbitals also allows for something called stronger London forces. Okay, we can also call them van der Waals forces. Van der Waals forces, or just stronger intramolecular forces. Sorry, intermolecular forces. Okay. And because of this electron, It conducts electricity because it's got this delocalized electron. It's slippery because the layers can slide against each other, but it also has a high melting point due to the fact it's still bonded to two other carbons, making 3, yep. And it's also insoluble for the same reasons as diamond in the previous slide. And the final allotrope is the Buckminsterfullerenes, or Buckyballs. They're super strong, they conduct electricity, and they scavenge for free radicals. All very good properties. And the Buckminsterfullerenes, or Buckyballs, basically they're C60, like footballs basically, with interlocking 6-sided and 5-sided rings. They have sp2 hybridization, the same as graphite, and they also have extra p orbitals to form pi bonds, so that means they conduct electricity just like graphite, but they also are stronger in terms of the covalent bonds and therefore can make stronger materials. And that was the allotropes of carbon. And we'll just finish off with sand or silicon dioxide, which is an example you used last year anyway. So silicon dioxide is a repeating unit, as every oxygen links to a second silicon atom, and it's basically like a glorified tetrahedral. Okay, very strong. And in terms of the difference between silicon and carbon, silicon is larger than carbon, so the silicon-oxygen bond strength is greater. Okay, the strength of the bond, the greater the bond length, the lower the bond enthalpy. So that means that it's actually easier to break. Therefore, silicon is more reactive than carbon or diamond. And that, in a nutshell, is what you need to know around the covalent compounds.